Alright, hello everyone and welcome to Handmade Hero, the show where we code a complete game live on stream. Today I would like to pick up where we left off last weekend and do a little bit of testing in terms of how we're doing our integration. So there was some confusion as well, and I just wanted to clear this up, just so everyone's kind of clear on what's going on. I'm going to go to the Blackboard a little bit and just say a couple things real quick because there was a bunch of confusion about this. Someone filed a GitHub bug report, which was not correct, which ironically mentioned a Stack Exchange thread that actually was correct. They just read the Stack Exchange thread wrong. What can you do? So we're going to talk just really briefly, because we talked about it before. I just want to re-emphasize it because I think it's not coming through. Let's talk about Hemisphere Integration. All right. So what we're doing here on Handmade Hero, in terms of solving for the lighting, right, is we have a hemisphere, and we're trying to sample the light over the entire hemisphere, right? So our goal is, if we had an infinite amount of computing power, we would literally want to check what the incoming light was in an infinite number of directions, everywhere on this hemisphere, right? And for each one of those, we would multiply the incoming light by an infinitesimal quantity, but that quantity would still be proportional to cosine theta. Why is it proportional to cosine theta? Because when you have light shining on a surface, if you imagine a beam of light shining on a surface, the degree to which it can illuminate that surface depends entirely on the angle at which it comes, right? So if you take a look at the aperture of light that will illuminate the same size on the surface, so let's say we've got this size here on the surface in question, if the light is shining directly down, you will notice that you get a much bigger aperture than if the light is shining in, right? This length is smaller than this length. How much smaller? Well, it happens to be proportional to the cosine of the angle, right? Because as this goes to there, right, we're gonna find that when we draw the triangle that says what that proportion is, right, the angle that we rotate this down by will change how long this length is, right? It's that part of the triangle, right? Wait, no. It's the wrong one. That part of the triangle. Sorry, I had that horribly wrong. There's a very bad drawing. Let me actually draw that out for you again, so you can see why. I cut the corner there and made myself do something horrific. I apologize. Let me draw it out full. I deserve it now. Okay. So in the case where we're shining directly on it, right, obviously it's going to be the same size. So that's going to be a 1, so that's not really that interesting. So the question is, as it comes down here, how much light is actually coming in, right? How much of the cosine is actually getting shown on here, right? And what we want to do is take a look at that angle, which is this angle right here. It's the angle off of this, right? And what we're looking for in this case is we're looking for figuring out what that infinitesimal shaft of light is that's kind of coming up like this, right? We're looking at a measure of that proportion that's changing as it comes down, and we want to figure out what that is. Now, in this particular case, right, we don't have any, like, the hypotenuse is sort of out of the equation because we're just talking about a hypotenuse of 1 here. We're just talking about, well, whatever the incoming value is. So we just want to know what the ratio is of whatever the incoming light is to how much we think would fall on the surface, right? And so what we want to know is, from this triangle, which we have just the angle of the light versus the normal, right? And I suppose I should draw that the other way around, because usually we would like to, although it doesn't matter which one we do because we can always change it, we would like to be able to just do one dot product and get it. So the angle we'd actually like to measure is this, right? So this angle here is actually sort of the inverse of this, right? It's the 90 degrees minus theta, right? Or pi over 2 minus theta, right? Because we know that this angle is pi over 2. It's 90 degrees. And so we know that we could look at either one of these, whichever one we want to, right? But this is the one that we want to do because if we are going to do dot product based lighting, where we have the normal pointing out this way and the light pointing out this way, we know that the normal transpose the light is the operation that's fastest for us to do. So we'd like it to be proportional to this angle if possible, right? Okay. So obviously, just intuitively speaking, this makes some sense then, because if these are pointed directly at each other, it's going to be 1, right? And in what it's going to be measuring actually in that particular case is it's going to be measuring this length, right? Which is completely 1. As we come down all the way to here, we know that this cosine, because that'll make this be pi over 2 when it gets to here, will be 0. Again, exactly what we want. We want it to go from 1 to 0, so it's doing the right sort of directional fall off. The question is it computing, is the cosine the correct fall off between 1 and 0 for the light, given that we're trying to do is measure how a shaft would change between here and here if the proportion was the same in the bottom. So assuming that we're talking about something like this, and we want to say, okay, if I were to construct one that looks like this, right, then I want to get an answer proportional to that. And if I was to construct one that looks like this, so, you know, as the angle comes down here, right, and I'm projecting essentially what this is, I'm projecting it over here, right, like that. Because when I dot product these two things together, that's what I'm going to get, right? I'm going to get the projection of this, and I should have drawn that a little bit differently. As it comes down, these are both unit length vectors, right? So as they come down, they're going to form a circle. I'm going to project this over, and I'm going to get essentially that value, right? So I'm going to end up measuring that thickness there, right? And so, in a sense, I mean, there's not a lot we can really say about that other than if you looked at how this was structured, since we know this was unit to begin with, right? We're talking about some fixed unit here, right? And we're talking about, you know, everything is basically proportional to 1 here. We're basically talking about a square, in a sense. And so measuring this fall off as we go down is going to be roughly the same. I know that's not particularly convincing, but if we imagine, for example, these looking like this, right, as they go like that, if that makes sense, then if we're trying to figure out what proportion of the light they're actually shining up, we could do the more complicated version of this. I'm trying to see if there's a good way I can illustrate this. If we wanted to construct this actual triangle here, right, what you can see is that there's a right angle that would be formed to find this length itself, right? And so we know that the angle in question is actually this angle because this shaft is bending down this way. So the right angle, let me draw that a little bit bigger down here so you can actually see it. Here's the original shaft of light coming down, and we're basically saying it's going to bend outward like that, right? And what we want to find is we want to find how this amount changed, right? How the width of that light that's coming in changed. And there's the, you know, there's the 90-degree angle. So if this angle here is the theta that we're measuring, right, then, you know, you can look at which angles are inside here and say, well, this angle is pi over 2, right, minus theta. Because we know that that angle is theta, so the angle that would complete the rest of the 90-degree turn is pi over 2 minus theta, right? And furthermore, we know that this angle has to, these all have to sum up to the total sum for the interior of the circle, for the triangle, right? So we know that we have this angle, which is pi over 2, right? That we know that angle's 90 degrees because we dropped it, it's perpendicular on purpose. We know that this angle is pi over 2 minus theta, right? Makes sense? And we know that the entire interior of the circle would have to add up. That's good, circle. The entire interior of the triangle would have the interior angles of the triangle would have to add up to pi. So if we actually want to know what this angle is, well, this angle also will end up being theta, right? Because if you take a look at what this simplifies down to, we end up with 2 pi over 2 minus theta, right? Or theta minus pi minus theta, right? Which is on this side of the thing. And we know that we need this thing to add up to pi, right? I got to actually put my, yeah. Did I say that correctly? I probably didn't say that correctly. Wow, I'm having a rough morning. I don't know why. Anyway, so yeah, no, I think I said that correctly. Anyway, doesn't matter. So anyway, when we actually look at what's going to happen here, the point of this is all just to figure out that, okay, so if we actually wanted to look at what happens when we take cosine theta, right, we do get this by taking cosine theta. It's just in a very roundabout sort of old trigonometry sort of calculation sort of way, right? It's weird because the angle that we're measuring is actually the one up here, which appears to not really be super related because it looks like your cosine theta term is actually going to take that, right? Because when you construct the triangle, you're looking at this triangle up here because this is where the theta is that we're measuring, because this is the normal and this is the light. And so it's a bit weird, but the reason that we're measuring that is just because if you actually go ahead and propagate the angles through, it ends up being the correct angle to use the cosine for to get this length anyway, even though that may seem kind of strange, right? So yeah, I don't know why I went on that tangent. Probably because I was so sleepy this morning, I made a sloppy mistake here and then felt like I needed the punishment. All right. So forget everything I just said. That was all just for me to reinforce the fact that we have to multiply incoming light by cosine theta in order to know how much of that light we can actually absorb or bounce as a surface, right? So whenever we take one of these incoming light directions, whatever the light value that comes in from this thing has to be proportional to n dot L in terms of how much light we actually receive. Now remember, this has nothing to do with how much light we actually want to reflect afterwards, because every surface has its own reflectance function, and this is not the reflectance function. This is just the light reception function. This is just the thing that says how much of the light we can get out of what's coming towards us from that direction. How much we reflect is a separate function that's about the properties of the material, right? Totally separate. So this is just a term that's about the fundamental nature of how light coming in at an angle cannot come in at as you cannot receive as much of it from a particular angle as another angle based on how wide that aperture is. So since we know this is the fundamental law, right, that no matter what surface we're talking about we have to obey, that means that as we take our integral, which would be a double integral over the hemisphere if we were going to literally take all of the incoming light of the hemisphere, right? We'd have two angles, who knows what they are. I probably shouldn't use those two. We'll just use A and B because theta was the angle we were using for the this n dot L here. So we have two angles, right? Let's say the orbit around and the azimuth, right? So maybe something that's like talking about how far around we go, and then something that talks about how far up we go to like make our to make our vector. So if we were to take the integral over the entire hemisphere, we would need to know some measure of the incoming light. So whatever that is, right? That's some magic function that we don't really know. that's proportional to A and B that we're trying to sample, but we always know that we would have to multiply it by n transpose L on the outside, which is that cosine theta term, right? So every sample we take or every integral we do would have to have that in there. And again, the reason for that is just because we're trying to mimic that winnowing of the aperture of light that can come in at that angle. So once we know that, this is what this always looks like. It always looks like some kind of a summation, right? If we were to do this discrete, it's just some kind of a summation. And you could think of the summation just virtually as a summation over the hemisphere, right? Even if we don't write it math-wise. If it's just like some summation over the hemisphere of n transpose L times some function on the hemisphere that we're sampling as much as we can, right? This term is always there. So what I was trying to say last time was, if you look at how this works, it's taking a sampling of things on the hemisphere and then weighting them by cosine theta, right? But since this sampling is not sufficient, right? Meaning we know that we're taking not all the samples. We're taking less samples than the total hemisphere. We're not doing a real integral, right? We're not accounting for all the light. Since we know this is a sparse sample, what we can do instead of taking a uniform sparse sample, right? One that samples the hemisphere uniformly. So one that kind of goes like, okay, let's just sample around this hemisphere and make sure that we sample very true, so there's no bias in the sampling. If we are going to do a uniform sampling of the hemisphere, then we have to multiply by n transpose L because that's what the equation mandates. But if we were to bias this sampling, then that would not necessarily be true anymore, because whatever the bias is will affect how we are summing the terms. Now, let me give you an example of this that doesn't have to do with hemispheres and lighting, because I think that's maybe where people are getting hung up. Let's suppose that we have a function that we know exactly what it is. Let's suppose it just looks like that, right? That's our function. Here's 0, here's 1, and it goes from 0 to 1 as well, right? So if we were to say, here's the x-axis, here's the y-axis, if we were to say f of x, you know, f of x just equals x, right? So as it comes up, we're just sampling it like so, right? Now, if I were to say that we had some reason why our sampling wanted to have an equation in it, right? So you can see this like n transpose L term was happening, right? So maybe I want to say that we want to sample this function, but our sampling, much like the hemisphere sampling, has some inbound law on it that's going to weight the samples, right? And let's say the weighting term is x. So when we take our integral or our sample summation, right, so our summation here, and we want to sample over all the x's, what we're actually going to do is say x f of x, right, is what we actually want to sample. So then what will happen is if we picked a uniform sampling of x's, right? If we said, oh, here, 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 and here, right? So we got like 0, 0.1, 0.2, 0.3, 0.4, right? We got like 10 samples uniformly spaced, right? And we summed those up. What we would get is a bunch of sums of x squared, right? Which is what we're dictating here, and what we expect. So we would expect to see essentially the integral from 0 to 1, right, of x f of x, which actually equals the integral from 0 to 1 of just x squared, because we know what this is. It's just x, right? We can substitute it in. Okay, so we can do that, and we can produce, we know what this is, right? We know what that integral would actually be, and we're trying to produce that integral, the integral of x squared there, right? But if instead we wanted to just optimize out this term, so we don't want to multiply by x anymore, right? Then what we can do is bias our sampling so that the bias lines up with how this term would have multiplied out. So think about it. The x term is going to mean that anything down here is not going to get weighted hardly at all when we sample, because it's going to be 0 or close to 0. So if we just don't take any samples out here and take a lot more samples up here where it would be close to 1, right? We're going to end up with the same effect because we're going to overweight the values that are on the high side and underweight the ones that are on the low side, thereby mimicking what x does, right? We're mimicking what x does. Excuse me. We are mimicking what x does so we don't have to multiply by it. Because as we move these samples around, we can make them line up in places where those samples will mimic the behavior of x just by virtue of their density, right? So if we make our sample density equal to our weighting coefficient, right, then we can just remove the weighting coefficient. That's all it's saying. If you have a constant on the outside of your integral or your sampling or your summation or whatever, if you, instead of actually doing the multiply, just move the samples to be the same distribution as that weighting would have done, then you're automatically going to have that same effect, right? Another way to look at this is, let's say you're taking an average. How do you take an average? Well, you take a bunch of things and you divide by the number that you got, right? So I take, 3 plus 6 plus 9, right? And I divide by 3, and what do I get, right? I get 18 divided by 3, right? Or 6, right? That's my average, right? And so if you think about what this kind of thing does, if you look at what we're doing here, we're essentially taking a weight, which is 1/3, and multiplying it by each of the terms that we're adding together, right? So this becomes 1, this becomes 2, and this becomes 3. You add those together, you get 6, right? Well, if I wanted to change my average to some kind of a weighted average, right? So, this was clearly, this is a continuous number line that we're doing here, right? Maybe I've got 1 plus 2 plus 3 plus, I need more numbers. 1 plus 2 plus 3 plus 4 plus 5 plus 6 plus 7 plus 8 plus 9. So if I'm taking some kind of an average like this, and I have a weight that I'm going to multiply by each of them, right? If I start with a uniform set of samples, right, in this case, and maybe this is like just the numbers from 1 to 10, right, or something like that. So if I have a uniform set of samples like this, then I would expect, and I multiply them by uniform weight, so my weight is going to be, well, I can't, okay, so let me get rid of the 10 there, right? Or maybe the better thing to do would be get rid of the 0. Leave the 10 in. There we go. And so if I want to go here and say, all right, let's take the average of these numbers. So I'm going to need 1/10 as my weighting coefficient, right? Then I'm going to get, 1/10 of 1, 1/10 of 2, 1/10 of 3, 1/10 of 4, et cetera, right? And so when I actually add these up, right? And then I divide by my weighting coefficient, then I get whatever my average point would have been, right? And I need the 0 in there to actually balance this out, but I ran out of room for it, right? If that makes sense. So, if I had added a 0 in there, then we would have had the 11 numbers and we could get the 5 out of it, right? Anyway. So if I take the numbers between 0 and 10 inclusive and I divide by it evenly, so each one of these got 1/11, and pretend my 0's back in there just because I want that even 5 for fun. Then you can kind of see, okay, all I'm doing here is I'm doing that same sum, right? I'm doing a sum of samples of x, right, as x goes from 0 to 10 in integer steps, right? And for each of those, I'm doing a weight, whatever the weight is, times my f of x, which is just x. And my weight in this case is just 1. So I'm just doing that average, right? Well, if now I wanted to change this weighting to what we were saying before, right? So my weighting is going to be x. So I have an uneven weighting of how I want these terms to go. Then when we do it, it's going to be a worse equation here, but we're going to get the same sort of thing, right? I'm going to get 1 times 1, 2 times 2, 3 times 3, 4 times 4, 5 times 5, 6 times 6, 7 times 7, 8 times 8, 9 times 9, 10 times 10, right? So there's my weighting. And that's my answer for that weighting, right? If that makes sense. And so what you can see there too is the weighting obviously gets a lot, it's much more affected by the higher numbers than the lower numbers because the weighting is higher on the higher numbers, right? So, you know, this is going to be multiplied by 10, and this one's only going to be multiplied by 1. So even regardless of what these samples are, this is going to have a lot more weight up there, right? So if I wanted to now, what I could do is skew my distribution so that I, instead of multiplying by x, I just concentrate all of my samples up here. I could do that. Now, one of the things that's a little bit confusing is we kind of have to deal with distributions that are going to be normal, right? So one of the problems with duplicating these results here is that we would want to normalize this number out first. So we'd have to know, okay, what's the integral, what are we actually dealing with here in terms of of the total amount of weight, right? Because remember, this is our total amount of weight is 55, right? So really we would want to look at that number, which is the normalized version. If you take a look at, because the weight wants to totally sum to 1, if that makes sense. So in this case here, we would probably say our answer was more like 7 because we'd really want to do something like the weight over the total weight, which in this case again was 55, right? So the idea here now, if we want to simplify this process, rather than multiplying everything by this weighting value, which is, some x over 55 here or whatever, which is, whatever the x is over 55. If we want to get rid of having to multiply by that value, what I can do instead is just sample what the function's going to be more heavily on this end than on that end, right? If that makes sense. And so then what I can do is change my weight back to a uniform weight, right? So instead, if I'm going to still take 10 samples, change the weight back to 1 over 10, right? Or 1 over 11 if there's 11 samples, however many we're going to take, right? Change the weight back to that, and then just sample biased by whatever the function we were using before, which is the x, right? So since we know that the x is going to be higher up here, you can even see, since the answer was 7 here, if we just take sort of samples that tend to skew up around there, we would end up with an answer in here, even though we're not actually multiplying by this anymore, right? And that's all we're trying to do with our weighting function. We're trying to observe the fact that when you take some function and you weight it by a certain skew so that it shifts towards some distribution of its numbers, right? In this case, you can kind of see exactly what would happen. Normally, it should have landed right about here on an even weighting of these values. Instead, it's going to land right about here because we've shifted it up by effectively squaring it, right? That's really all that we're talking about. Taking samples that look like that and turning them into samples that look like that, right? So that we get answers that shift upward. Anyway, I realize it's kind of a weird thing. I'm not sure how to write the more mathematically concise version of it because it's a discrete process. So, I mean, one way to think about it would be that the sampling function that you use has a bias in it, and you could think about that bias as being written into the equation. So, for example, if you were talking about it like this, so here's our hemisphere sampling. So if you were talking about it like this is the function that you're doing. The reason that this FAB just looks like an FAB term is because the bias is assumed not to be there. So like it is assumed to be no sampling bias, right? But if you imagined writing the sampling bias in it, so let's suppose we were going to replace FA of B with a different function, right? GA of B, and GA of B equals FA of B, whatever the function was, but it's biased so that its results come back with the inverse sampling, right? So they come back proportional to 1 over cosine theta. Then you could see that when you substitute this in, right? I guess that's kind of not exactly the right way I should have written it. Let me write that slightly differently. Let me write that the backwards way because I think that would be a little better. So if this is the integral that we want, we're saying we essentially want to know what we would have to produce here, right? If we wanted these two things to be equal. Right? So we want to take an integral of some function that will equal the integral of this function times the cosine theta, right? And so when you look at these two things, it just means that GA of B has to equal cosine theta FA of B, right? And then we know in order to figure out, what this function has to be, it has to be the cosine weighted version of this, right? That's just what that ends up being equal to, right? It's exactly written out, in that way. So if we can come up with another function which just happens to have that bias already built in, then we know that we wouldn't have to do this anymore, right? We wouldn't have to multiply it because the actual function actually has it in there already, which is why we say that if we took our sampling and biased it so that it takes samples close to where the cosine theta is 1 and very few samples close to where cosine theta is 0, which is down here, right? That we expect to get the same answer on the way out. Hopefully that makes some sense. I don't know, I probably did a horrible job explaining that. It felt like I did. Probably because I'm not a ray tracing guy. So if I spent all my time working on this, I probably would have thought of good ways to think about that that are clearer to understand. But I'm not. So what can you do? We tried to do this at the end of the previous stream, and we haven't quite gotten there yet. So if you remember what we were doing in the code here, let's see, we put in, here we go, generate lighting pattern. So we put a little thing in the code here that just tried doing these samples. You can see them do it. We didn't quite get stable enough results, and we don't really know why. Now, there's a couple of reasons we might not get stable results. One reason might be that we are doing things correctly, and we just aren't taking enough samples. Another reason is we have a bug, right? And so we need to investigate this a little bit further. What I'm going to do first, so if you take a look here, this is the random bilateral samples. I want to see what happens with the minimum maximum testing if we just crank up the sample count really dramatically here, if that makes sense, and take a look at what the average is at that point. So in this sample count here, I'm going to just crank it up massively, like so. And I want to see if this converges. And this is just taking random samples, sampling a... here we go. Sampling a pattern of randomness and looking at what the minimum and maximum averages are. what is happening, and then not terminating. Is 1024 too much on that? What's our sample count? That's kind of ridiculous that that would be taking that long. What's happening here? This is a very slow function, but I guess it is taking that long. Oh, you know why? Because we're actually doing 1024 tests of it. So that, all right, I agree. That may have been a little bit much. Let's tone it down a little, but only a little. We could also just compile with optimizations on, I suppose, but... All right. So I just want to look at what these values are. So the sample count here would also have to be higher to get the actual average right, but I still, so something seems a little bit off, because I feel like once we take enough samples, we should be getting a fairly accurate result, unless it might be that our random number generator isn't great either, but we'll see. So let's do less tests and more samples. I want to like densely sample the hemisphere, right? So now our sample count's 4,096. We have a lot less tests, but here's our min test average and here's our max test average. And what you can see is they're still pretty bad, right? They're still fairly divergent, which again makes me wonder, like, if we've got something habitually wrong happening here. I'm gonna keep upping the sample count. And I just want to see, okay, so they're starting to converge more at a very, very high sample count, right? Let me run more tests and make sure. Yeah, so, okay, so basically at that sample count, at 65,000 samples, we start to converge on an answer, right? Which is pretty bad, right? It's not great. And that's a smooth function that's easy to integrate. That just, I guess, goes to show you just how hard it is to integrate over a hemisphere, unless there's some kind of bug here. Now, the other thing is we don't know how our random function is. So, you know what I'd like to do as well? Since we've got, right now we have XOR shift in there, but XOR shift is not particularly good. Right, here's our XOR shift. What I'd like to do is I'd like to go ahead and see if we can do a more precise version of that. Maybe taking the PCG stuff, for example, and having one of these that works a little bit better. So, if I remember correctly, I want to check because we are taking a set of these together. And I seem to remember there being something that needed to happen. That is what we're talking about. So k-dimensional equidistribution is just talking about the fact that if we were to take several of these numbers and make sure that if we use them as Euclidean parameters, right, like x, y, z, that they produce equal distributions in space. And we actually do care about that in this case, right? And what you can see here is it says, you know, that there's something specific we need to know about that. I'm not sure where it talks about that. Let's see. Although we can achieve very long periods of k-distribution for arbitrary k using the counting system, there is a better method of illustrating extension method. Suppose we have a b-bit generator producing r-bit values, which we shall call the base generator. The extended generator consists of those b-bits of state and k additional r-bit values, which we shall call the extension array. We use the state of the base generator to choose a value from the extension array by passing the base generator state through a selector function. The final output of the combined generator is produced by XORing the selected value from the extension array with the random number produced by the base generator. Restated using the formalizations. So we need sort of an out-of-band thing for that. Selected function can be an arbitrary function, but for simplicity, let us assume that k equals to the x, and that selection merely drops bits to choose x from the state. Two obvious choices for choosing x bits are taking the higher order bits and taking the lower order bits. If we wish to perform party tricks like the ones just in section 434, so use lower order bits because they will access all the elements of the extension array before any elements repeat. So we have an output function that uniformly maps the state of the combined generator. We must define how the extension array advances. In figure 16 table 1, PCG XSHRS 6432 is shown with 2-dimensional and 1024-dimensional equidistribution using this mechanism, X2. So we're mostly interested, we don't need quite so much, but let's take a look at, where is that? Oh. Figure 16. I don't know where figure 16 is. Here it is. Well, unfortunately, I don't see any. I don't really see a lot of, like, there's no plotting in here of exactly how bad it would be if we just used a basic PCG versus trying to use an extension array. I guess what I would want to do is I want to go ahead and take a look at this random bilateral, and I would like to plot it, if that makes sense, so I can actually see what's going on when the sampling density gets up higher. I'd like to see what the density is, if it tends to be very clumpy or not. And then if I was to improve the random number generator just for the version, just for this test, would it change? That's what I want to see, because I'm not sure I have a good sense from the paper just how bad the k-dimensional distribution is if I don't do the more advanced version. So yeah. So if I wanted to draw this, we already have the ability to output these points, right? I'm doing it here, essentially, with this sample points situation. So if we, I assume, run this, and I could probably get rid of the test case now as well, but we should be seeing somewhere in here yeah, there they are, all of the points getting drawn, right? And so those are, it's currently drawing our sample points. What I want to do is have it draw random points, and I just want to see what that looks like. So if I if0 this out here, and I make one of these, what I could do is just say like, all right, let's just write those to a table when I generate them, and then I'll draw them. I can't draw quite so many, but I'll draw some, right? In fact, I don't really want to copy this one. I want to copy this one. So if I imagine taking this test series here and doing exactly the same, I'll literally copy the code here from that init. Oops. So this, we'll just go ahead and draw that. There we go. So yeah, that's it. I don't really want line segment. But there's my direction. And here's where we'll draw it. So if I go ahead and say we've got draw point count, let's say we draw 1024 of these. I don't know if that'll blow out how much buffer space we have, but once we push one of these on, the start point can stay the same. The normal is just direction here, and I think that should basically do it. And I suppose the other thing I don't really know at the moment, unfortunately, is I don't actually know whether this is a fair way of generating hemisphere points. So I may also be creating a problem that way. I'm not sure. So let's play around with this a little bit. All right, so if I do draw point count here, so we can draw like a lot of these. You can see the sphere here. And, you know, would I immediately say that it's got a problem? I'm not sure, but it kind of looks like it might. just in terms of whether that, how good that random covering is. Like I said, I don't really know whether this is a fair way of producing points on a sphere. I could take a look. It's incorrect to select spherical coordinates. That's okay. We don't do that. So they say spherical coordinates proportional to this is one way to do it. So they definitely give ones here that do it. Three Gaussian random variables, x, y, and z, then the distribution of vectors is this. So we're definitely wrong. Because we are not picking Gaussian, we're picking white noise on -1 to 1 in theory. In theory. So for uniform distributed random numbers, they're suggesting you do this and then that. Right? So we could just do this as pretty straightforward. Right? So maybe let's try this and see. I'm just curious. You can see what that one looked like, right? So let's do a little F0 here. Ooh. All right. So it wants two random numbers, x1 and x2. And those are both supposed to be random bilaterals, according to the text. Oops. According to Marsaglia, or Marsaglia. Yeah. George Marsaglia. From Ohio State University. All right. So if we were to follow his formula, then we want to reject pairs that have a length squared greater than 1. So, oops. And it says reject anything that's greater than or equal to 1. And then we just generate the points directly, supposedly, without normalizing, because the normalization is already built into the equations. So our x is 2 times x1 times square root. And it looks like that value is actually the same. So let's just call that, I guess let's call that root. So it's 2 times x1 and then 2 times x2 times the same root term. And then z is special, as it always is. And that's just x1, yeah, so it's actually this term right here. And that's, in theory, the algorithm, if I didn't make a mistake in translation. And we can take a look at what that looks like. And I wouldn't say that that looks any different to me. I would say that looks about the same. So given the fact that I'm seeing roughly the same thing with both of these, oops, I did that a little bit poorly there. Yeah. Now I should be able to run either of these. So yeah, like looking at that. And looking at that. I mean, they're definitely different. Oh, but you know what? This is doing the whole sphere, and we only want the hemisphere. So I suppose in that case we have to modify that formula a little bit differently, right? Because in this case here, the z value can range, you know, all the way, and we don't really want it to do that, right? So we want this term here we want that term there to only be able to go up to 1. Sorry, go up to 0.5. So I believe, and yeah, we never want it to get all the way up to 1. So I believe that the correct modification to his routine is that for a hemisphere. And so that's the hemisphere version, right? You can see what I mean by that, because you can see here, in this case, the z coordinate is 1 minus 2 times square, right? And so if you normally let this value go from 0 to 1, this will go from 1 to -1, which would be the whole hemisphere. But if we just cap it so it can only go from 0 to 0.5, that will make this go from 1 to 0, which gives us a hemisphere. So I just made that slight modification to his routine. Pretty basic. All right, so, you know, that's what that routine looks like. That's what our routine looks like. I don't see a lot of difference there. At least visually, nothing jumps out at me. So I'm going to just double check what happens if we change our random number to a different... I don't know what I want to call this exactly. But in our randomness, you know, we have this one, which is just using an XOR shift. And what I want to do is create a different one that's a non-XOR shift. Well, I shouldn't say a non-XOR shift. That does the PCG version. And in order to do that, what I'm going to do is say, okay, let's say we've got a random series PCG here or something. In fact, I could just say random series PCG and then just have the functions work the same. So if I have a random series PCG, this one will operate on something fancier. We'll try putting the state in like so. And we'll have random next to 32, much like we did. All right. So what we want to do here is I'm going to start with the same thing that we had before. But I'm going to try and do a better random number generator than the one that we had. And then we can swap between them and see which one works out. So if we go ahead and... so we've got two ways of picking things on the sphere we can test between, and now we can test between two different random numbers as well. And then I can just see to convince myself that we're okay. So 32-bit output, 64-bit state is what I wanted. And the reason that I want that is because 64-bit state with 32-bit output on PCGs is like the better in terms of randomness. It performs better because it has just more bits to store as it goes forward compared to the number it needs to actually generate. So let's pick this one because it's the most random one. This one is more for speed, I guess. So we'll see. So let's see. Strategy for an XOR shift to improve the high bits and randomly rotate all the bits with 6 bits of state. 32-bit output function to be coded tersely as this. And so the rotation, we do have in this case, it looks like I guess the idea is that the rotation only happens on the 32-bit output, which is actually kind of nice. I didn't quite realize that. I've never done this one, the 64-bit, 32-bit. Because if you look at the way this is written here, the 32-bit rotation doesn't ever have to update the 64-bit state. So you never need a 64-bit rotate. Which is kind of nice, because I don't know if there is a 64-bit rotate on the x64. There might be. I've certainly never called it. There is a 64-bit rotate, I believe, though. I mean, a 32-bit rotate, I believe, if I remember correctly. This is neither here nor there, because a rotation is actually not hard to code in emulated, basically, right? Because you just do multiple shifts and order them together. But it's just kind of interesting. I didn't know that. So anyway, if you look at what's happening here, right, it's taking the sort of a fairly straightforward thing you're doing here, which is the state XORed with itself shifted down 18, shifted down again 27, and then it's taking and extracting the high bits of the state, basically bits 59, 60, 61, 60, 61, 62, 63, and it's using those to create, no, I was right, sorry, 59, 60, 61, 62, 63, to create a number between 0 and 31 to use as the rotation, right? So it's using the high bits of the state to rotate the low bits of the state, basically, if that makes sense. And then here's a version of that doesn't use a rotation. It says here it has slightly worse statistical performance, but it's got slightly better speed, right? So yeah. So anyway, if we look at this one, this is pretty easy to implement, right? It's after we're going to have to do our XOR shift part of this, because we got to do an XOR shift 64 here, right? So we'll do that in a second. But once we have the result, should probably just call this the state. Once we have the state vector, the idea behind these permuted random number generators is just to take a random number that isn't particularly good, like the one that comes out of XOR shift, which we'll do in a second here, right? The XOR shift goes here. What we want to do is take something that was like a 64-bit XOR shift, and now we want to make it a much better random number by using the bits in it to produce a better random number out of it, right? And that's what these PCGs do. And so what they do is they say, all right, let's take it, let's do the state XORed with the state shifted down by 18. And then what we want to do is shift that down by 27. And then what we want to do is do the rotation. I lost my place there. Sorry about that. Here it is. And then do the rotation by the top bits. Like so. Now, we have a rotate, as you can see. I don't remember which one she wanted us to do. Clockwise rotation. So I guess I would interpret clockwise rotation as a rightward rotation. Not sure what clockwise means in this case, but I assume it means going this way. So I'm going to go ahead and say it's rotate right. Like so. And so in this case, after this has been done, we want to convert this to a U32, because remember, this is actually a 64-bit value. And we want this to be assigned value, I guess, in this case. This will not give us a signed result, so it should never be signed, but that's just, this expects an integer anyway, so that's just what we're going to have to use there. And so then I believe this gives us the result that we want here. Let me go ahead and give a compilation here. I did. There we go. And so now if I want to actually do the random bilateral version here, which is this, I can take these two, and these are the same, and the only difference is which kind of random number generator it's calling. So this should be exactly the same, right? So now we have one that uses the PCG there, but we are not actually producing the XOR state here. What is this saying? So we need to implement that. Unreachable code. Oh, because it actually figured out that this wouldn't terminate? That's amazing. Is that actually what it did? That's kind of amazing. It figured out that this would never produce a value that would pass this check because that was a constant. Dude, that is awesome. Right? I mean, the compiler actually figured out that because we never modify that state value, that we'd never get out of this loop. I think that's what it did anyway. All right, so let's take a look at, we need an XOR shift 64 now in here. Let's see. That's a 128 XOR shift. But what is the 64-bit version of XOR shift? We have a 32-bit and a 128. Unless that XOR shift 128 is actually 64-bit. No, it's not. It's a, that's correctly Am I missing something there? Maybe they're oh, well, maybe they're only talking about XOR shifting only the top 32. I'm not sure. If we were only going to use a 32-bit XOR shift, and it doesn't look like there is a 64-bit XOR shift, only 128 and 32. I'm not sure exactly what she's referring to in here. Let's take a look back. So let's take a look. Here's an actual implementation. So the magic constant there is a little odd since it's not explained anywhere. This right here is the rotation as you would expect the rotation to be. So this part is exactly what we wrote here. This rotate right. Right? In fact, let me isolate it for you there so you can see what I'm talking about. So this internal value, if we just grab that out of here, so this right here is just taking that right there. That's the rotate amount, right? And you can see it doing a rotation rather than calling the actual rotate on the chip, because that doesn't exist in C. She's just doing the rotation manually. Remember I said a few minutes ago you don't have to worry too much about that because you can just do it yourself. But since we have a 32-bit rotate, we can just use it. It's not a big deal one way or the other. So this part right here is the part that we're interested in. And you can see that as far as XOR shift is concerned, it's just doing that, right? So the XOR shift part is exactly that's the exact part that we wrote down from the equation that she had there. So this is the only part that I'm not sure about, right? I don't quite know where she got the magic constant from to advance the internal state there. Looks like if someone wants to implement it in Java or Rust. I don't know if she's taking contributions. So yeah, so I'm not sure about that one part right there, but I guess that rolls the XOR shift into it. And I guess... yeah, I guess I don't understand. So I would like to see a more full explanation of this part right here. So for example, this RNG Inc. or 1, it's not really discussed what that is or why you would OR it with 1, because you could have just stored it ORed with 1. So there's more to it than that, right? Like that's not a complete understanding of what's going on there. I don't imagine there's any more comments in here, but if there are, of course it is. Let's take a look. Because I'd like to understand where that's coming from. I don't really like it when I don't know what something's supposed to do. I feel like that just leads to problems. Hello, Windows. Maybe I won't create a folder. Okay. Anyone want to explain what's happening right now? Anyone from Microsoft? What is happening right now? Let's kill Visual Studio for starters. So this is still working. It's just So maybe Explorer needs to get... There we go. My lord. All I wanted to do was unpack this file. Can it do it now? No. So I just can't hit new. Okay. I just don't even know what to say. Windows. It can't even create a new directory anymore. Unbelievable. Okay, so here we are on the W drive. I'm going to just make it from the command line because apparently that's all we can do. I will go ahead and... do we have a 7-zip command line? We do, I guess, but it's not in the path. I'm going to see if I can unzip it using Explorer. Hope springs eternal, I guess, at this point. And we'll just see if that'll work. So here I go. Hey, what do you know? Ladies and gentlemen, Microsoft. Every version of Windows, they break something new. All right, so if we want to take a look at this, because I just wanted to see if there was any more explanation in here of where the magic constants are coming from, like I assume there's some kind of a fold down of something talked about in the paper, you know, for optimality or something like that. But if I take a look at what's going on here, let's just take a look. So it looks like in the actual implementation in here, it does do exactly what I said, which was ORing in the 1-bit pre. So you notice the OR does not appear here. I don't know why her other version doesn't have that. Probably because she wanted you to be able to put anything in there, even an even number, and then she would just put the OR in there. So this is probably just more optimized version for when she knows she's the one who initialized the values, I guess. Because this is the more sensible way to write it, and that is how she wrote it. So I'm not sure why that other one had something else going on. Unfortunately, we still don't know really where that came from. And we're really no closer to knowing. I mean, I guess she just picked a basic linear congruential generator there. Is which one of those was picked talked about in here? Let's see. So that number itself appears nowhere in the paper. But it might be just referenced in the paper to a previous random number generator that uses that constant. So yeah, I mean, this is just an LCG step, but I just don't see where in here it talks about the particular choice. I mean, we could look in here for the multiplication for good LCGs 25. So we could look at that reference. Let's take a look here. That may not be online though, unfortunately. Oh man. All right, this search isn't going to work. It doesn't correctly identify those numbers. That's weird. That's pretty funny. So yeah, it doesn't appear to be a direct pull from this table, but it could be a fold, you know, of constants from this table. So it's hard to say. Yeah. So we're going to have to do some more digging if we want to figure out where that's from. That's the only part that's a little confusing here because I'm not really sure how this LCG... So, you know, the XOR shift is pretty clear, right? But this particular LCG update step, I don't quite know. I don't quite know where that's coming from. So I guess one thing I could do is search for it. Oh. Interesting. So there's our answer. So it's actually from the, I guess, original Knuth version here, although I guess it's actually this one, since the increment, he has an increment and we don't, if that makes sense. So I guess we're actually talking about this one more directly, perhaps, because it sounds like the increment version, which is this, is actually fine to be anything in our version, where it was a specific version in the MX one, right? So I guess that gives us everything we need to know. Basically, those are all our pieces. We're doing the Knuth style linear congruential generator, followed by an XOR shift, followed by a PCG rotation, or shift and rotation. And I think that's it. So in theory, if I want to improve the quality of this thing, then I should be able to do so. The basic version of it would look something like this. And then we don't actually really have a use for this right now, but it could. What that sort of suggests to a certain degree is that if we want to pick those random numbers, we may want to use 3 different streams for better k-dimensional distribution, right? Like we were talking about before, in order when we pick our x, y's, and z's, maybe a better way to do that would be to pick them from 3 different stream selectors so that they're not picking from the same series in order. So put that out on the table. This state update, we can use the old state as does she, because again, she says to maximize ILP. What she means by that is instruction level parallelism. The idea here is that if we use the state as it comes in, we're getting the previous random number generator, the previous random number in the series actually. We don't care whether we use I-1 or I. And the point is, these computations can start before this one finishes that does the update. So it's just better to use the old state than the new state, right? Since we don't care whether we use, random numbers 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, or 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. We don't care which one we use. We might as well always use the one that's one back, if that makes sense. So I think that's basically it. And yeah, I think that's basically it. So I want to go ahead and take a look at the version of this now when we do this. And how much time we got? I got 15 minutes left. And that all looks pretty good to me. So I think that's fine. In order to random seed one of these things, though, we have to have a seed function here. How are we doing this before? Yeah, we had random seed. So we need a random seed PCG, basically. One of these, and that takes a state and a selector. And the idea here, again, is that when it's doing the increment, it really wants to toggle that bottom one on and off, it looks like. Because again, the 1 always gets ORed in here. So it's a 1 and then any other random bits you want. But you're not allowed to ever have an even number as the incrementor for whatever reason. So when we do a seed, the state equals the state, and the selector equals the selector, but we're going to shove the selector up into the... We're going to move it up 1 place when we get it, and then make sure the bottom bit is always 1. And remember, that was the part that was a little weird about why it was being done in the external code. That was this part. This. That was the part I was like, why are we ORing it every time? And I guess that's just so you can put anything you want in here, but it's a better way, obviously, just to OR it first, and then you don't have to do that every time, right? So there's no reason not to just do it like that. All right, so if we took that... I'm making up complete nonsense there. Hold on a second. Let's see if we get any better results here. We probably should test these random number generators at some point as well. But I just want to take a look and see. Oh my. That's awesome. That is extremely cool. Not what we wanted, but very interesting. So I have to go, yeah. I have to go back over here and make sure I didn't mess anything up here. So these, I think... I don't see anything weird happening here, although I don't know if I have to make sure it will do this in 64-bit, though. But I think it will. This is wrong. And probably had a lot to do with it. Yes, unsurprisingly. So that is the PCG version of things. And in theory, I wrote this so that we can just swap between them by changing this to not be PCG. Does it look a little better? You know, maybe it does. But again, not horrible. So I guess on the whole, it's pretty hard to say. I don't see a lot of difference among these random number generators for our purpose. Let me also try one more thing before we conclude for the day. Let me try having a different series for each of these. Wow, that was an incredibly non-random set of numbers to put in. Because I'm just curious what happens if we do that, if there's any major difference between those. Oops. Or if it mostly looks the same. And I honestly don't see a lot of difference. Oops. So, I mean, I could believe that there was a imperceptible difference between those two. I cannot believe that there is a significant difference between those. So, as far as I'm concerned, I don't think we really care. I mean, it looks fine. The non-PCG one looks just as good. So as far as I can tell, that part is just not super relevant. Like, it doesn't look like our randomness could be really doing all that much damage. Maybe there's a slight bias there, but it really just does not seem particularly bad to me. So yeah, I'm gonna go and go to the Q&A because the next thing we're gonna do then is just go back to the other routine there. So I'm pretty satisfied that the randomness doesn't really make a difference there, unless I did something wrong in my test. But visually speaking, if there was a strong difference between those two, I should be able to see it. And I don't see it. So that part, yeah, we'll see. Look, Thor, you can't have an even number as a selector because then the ones bit would never flip and your period would get cut down a few orders of magnitude. The paper goes over that at some point, if I remember correctly. Yeah, I guess that's true because the XOR shift doesn't modify the actual state value. When you write the state part, did I have a typo there? Oh, I do. I do not know why I typed it that way. Let me double check to make sure that didn't make a significant difference. I don't think it will, because actually that selector can be any value, I believe. Here's the normal version. So that's using the old way. Here's the PCG version. And again, pretty similar looking. If anything, I would have called it worse, for our purposes anyway. Let's try, yeah. So I got nothing. So yeah, so I think like what seems to be the case here, unless I'm missing something, is that our particular choice of entropy doesn't really affect this much. And Lucas says the basic PCG32 you're using will only be k-dimensionally equally distributed for simple U32 to U32 tuples. Each U32 will appear 2 to the 32 times within the 2 to the 64 period. You'll need PCG64 or an extension array if you want KD equidistant for V3 or more. However, it probably doesn't actually matter for your V3 generation because you're unlikely to see the generator loop around. Yeah, the generator can't loop around in our case, right? What is your opinion on event systems and how would you implement one? I'm sorry, I'm not sure what you mean by an event system. That's a pretty broad term. Can you be more specific? Is there a way that a Slack channel can be set up? That way us newbies can catch up and have a place to ask questions, as I'm finding it hard to keep up with the earlier videos without a lot of side researching. Well, there are forums, if that's what you mean. Are you talking about actual like voice chat or something? What are we sampling in for what? I missed out on that part. We are just trying to make sure that our lighting sampling is correct for our lighting system. So why opt for PCG or LCD generator rather than just hashing the time for a random number? Well, because hashing the time is incredibly expensive. And also the time is not random. If you use it, you know. Let me state this alternately. So let's suppose you get the time. The time on the system will only be accurate to a certain degree, right? So if you want it, so time, meaning the actual time, you're only going to get it once every, millisecond or something, or, the actual system time is not accurate to very high, right? It's less than a millisecond. It's probably lower than that. But so you'd have to be talking about like RDTSC, and RDTSC isn't random. So hashing it to make it into a random number would just be another exercise in having a random number generator, right? So you'd still have to do all the work. You're just doing extra work by calling RDTSC, which you don't need to do because it doesn't add entropy, right? I don't know if that makes any sense, but... Oh, an event system for communicating between interacting systems. I mean, I don't know that there's really much to say about it. It's just a enum that says what the event is, and then a package that has the information in it. I don't know that there's a lot to it. I don't tend to think of that as a particularly important thing. Like, if you've got two systems that need to communicate, just whatever they're trying to communicate, I just usually send it directly in a linked list queue or something. That's really all I do. I don't get particularly fancy. In Monte Carlo estimates, usually error scales like 1 over square root samples. For 1024 samples, one expects error in the order of 0.03, and for 65,000, one expects error on the order of 0.003. It therefore seems that the error you're seeing is pretty reasonable. Yeah, it might be, but I don't know. Like I said, I wanted to make sure we didn't have any problems first before I conclude that it's okay. What would you consider the most performant RNG despite the accuracy? I don't know. I'm not an expert. I know almost nothing about random number generators. So I really couldn't tell you. I use XOR shift myself a lot because it's simple and it's possible to do it in SIMD. PCGs you can't do in SIMD really because variable shift isn't there. So like if you're doing SSE 2 or 4, you can't do a variable shift. So yeah. What will you work on tomorrow? I'm just going to take a look at the difference between our... I'm going to rewrite those other routines that we're finding our integration test, and I'm going to make sure that they tend to converge to the same output, because right now I think I suspect, and I could be wrong, But I suspect that the criteria for blue noise thwart the cosine distribution. So I think we need to generate blue noise on the sphere directly and then have a cosine weighting. I'm pretty sure. I'm just guessing, but I believe we have a problem of the following form, and I want to track it down before we go any further. So I believe we have a problem that looks like conventional wisdom is, well, if you want to generate cosine theta distributed points on the sphere so that you get more points at the top and less points at the periphery, right, pointing this way. If you want cosine and a cosine theta fall off of them, then what you need to do is you generate points on a disk that are equidistributed, and then you project them up to the hemisphere, which is what we did, and that gives you a cosine weighted distribution. Now, that is if the points in the disk are randomly chosen. But blue noise isn't random. Blue noise is blue noise, not white noise. So this is for white noise. And white noise is just wherever, right? It's completely random. Blue noise, if we look at the disk, it forces things to be spaced reasonably. Right? What that means is there will be more points on the outer edge, right, than on the inside, because as you get further, there's more area of the shape towards the perimeter than there is in the center. That's just the property of solids, right? So for a k-dimensional shape, the higher k is, every as you go from 1D to 2D to 3D to 4D to 5D to 6D to 70 to 80 to 90, etc., 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 more and more of the total volume is at the border, right? So it's not that bad in 2D, but it's bad. It's worse in 3D. It's very bad in 4D. By 5D, 6D, 7D, all the shape is at the border. All of the volume is at the border. All of it, right? It's why, you know, it's the standard pizza thing, right? If I take a look at the if I take a look at a circle, if I take a look at R, half R and R, if I take a look at these two circles and I say, what's the area of the outer side and the inner side, right? Well, pi R over 2 squared is this thing, right? Pi r squared is the outer circle, so this is the inner circle. This is the outer circle, right? So the area of the inner one is pi r squared over 4, right? Does that make sense? Because it's pi r squared, and r in this case is r over 2, right? Whereas the outer circle is pi r squared, but the area in here, this part is going to be subtracted away. So it's actually pi r squared for the ring. It's pi r squared minus pi r squared over 4, right? Otherwise known as 4 pi r squared over 4 minus pi r squared over 4, which is 3 pi r squared over 4, or 3 quarters pi r squared, right? So the inner one is 1/4 pi r squared, would be one way to think of it, versus 3/4 pi r squared, right? And like, which one of those is bigger? Well, like that one, right? So what I'm trying to get at here is that if you look at how this distribution ends up being weighted, if we assume that we are forcing even coverage across the whole thing, there's a lot more points in that outer ring than in the interior. Whereas if we were randomly picking points, I don't know that that would necessarily be true. It probably is, but I'm not sure. So I can't say for sure whether the fact that we have an equal coverage biases things towards the outside because there's more room to put them out there, and we're going to put them out there, as opposed to if we just randomly pick them. So this should be true for white noise or blue noise, I think, but it's pretty complicated, and I can't guarantee that. I just don't know if it's true. And so without looking into it, I can't say for sure. Can you see the current state of the lighting? Yes, we do have a test we can move around here. So the white area outside is the area that's outside the visible region in the game, so we aren't running the lighting on it, and the inside is the area that we are running the lighting on. I can move this light around so you can kind of see how that lighting is being calculated. Right now, we're not really using the lighting points maximally because the renderer doesn't really use them distributed the way that it should. So we will be doing a few things to make it smooth through here, which we may or may not want. I don't know how much we want to reinforce the blockiness of the game's geometry. We may want to reinforce it, in which case we would not do what I just said. But, you know, there you go. So the lighting seems to be working pretty good right now, but we just don't have a handle on whether our sampling weighting is correct, and so that's the part that I wanted to take a look at, right? Is there an intention to support shadows from the point lights? No, because we don't have any point lights. We only have area lights. So we just use diffuse lighting right now, and we're not going to do direct shadowing. And again, that's because we don't currently have a concept of a light source. Everything in the game is a light source, in a sense. So lighting comes from everywhere. Any ray marching volumetric fluid stuff? No, I don't think so. All right, looks like we are out of questions. All right. Thank you, everyone, for joining me for another episode of Handmade Hero. It's been a pleasure coding with you, as always. If you want to play around with source code at home, you can always pre-order the game on handmadehero.org, and it comes with the source code if you want to play around with it. Tomorrow, we will take a look at the actual integration thing again and see whether or not we think we need to modify it in some way to make it more accurate. Because right now I'm still a little concerned that it's not really doing a properly cosine weighted distribution on the sphere due to what happens when you project blue noise on a disk up to a hemisphere. I'm just not sure about it. I have a bad feeling about it. So that's what we're going to take a look at. I think we've eliminated the entropy source as a problem today. I'm pretty confident that we're not having any significant error coming from that. So I think we can just rule that out now, and we can just look at the blue noise projection part and figure out if that's okay. So that's about it. I'll be back here tomorrow. Hope to see you all for that. Until then, have fun programming, and I'll see everyone on the internet. Take it easy, everybody.